Example 1222b says compare HBr with KBr. Which has a higher melting point and why? All right, so if we just look at HBr by itself, we need to decide what type of bond is holding it together. So technically, it is polar. It's not considered hydrogen bonding, so this would be dipole-dipole. Much more important, it's an IMF, so it's an intermolecular force. And then KBr. So it might be tricky because technically when we're considered IMFs, like in the beginning of this chapter, we looked at an ionic combined with a hydrogen bond. But right now we're just looking at just KBr by itself. So what is holding it together? Just an ionic bond, and this is not considered an IMF. If we were asking these together, HBr and KBr, then it would be an ion dipole bond. But since we're looking at it by itself, it's just an ionic bond. So the next question would be, which has the higher melting point? So which one has the strongest bond out of the two? And that is going to be KBr, because what's holding the KBr together is much stronger than intermolecular forces. So if we go back, intermolecular forces are temporary and they're much weaker than ionic. Example 12.23 says, state the type of bonding or force holding together each of the following solids and indicate whether the melting point is low or high. So before we think about the melting point, we need to identify what type of metal each of these are. So silica dioxide, because it's just not a metal by itself, it's not going to be a metallic solid. Next, it's not considered a molecular solid because it's not being held together by IMFs. So if we go look at the 4 different types of IMFs, silica dioxide does not follow in those. The next will be ionic, and since it's not an anion and a cation together, it's not going to be an ionic bond. That leaves covalent. So this is going to be a network covalent bond. Also, this would be when you can go look back at that table, and this is in that table. So if you're at all confused, you can always go relook at that table and see where silica is. Also, it's important to note that covalent networks have a very high melting point. Also, you can find in that table. The next is potassium chloride. So potassium is going to be in the first column of the periodic table of elements and chloride in the 7th. So this is a prime example of an ionic compound. So this will be an ionic solid. So ionic solids have high melting points. Not as high as covalent network, but still very high. And lastly, ammonia. We've discussed ammonia. This one has hydrogen bonding, which is an IMF. So IMFs means molecular solids, and that means it also has a low melting point. Let's talk a little bit more detail about metallic solids because technically they're so diverse depending on each individual metal. So it's important to note that when we're saying metallic solids, that means that we're just looking at one individual metal with itself as a solid. So they neither transfer nor share electrons in that solid, but instead the valence electrons surround the metal cation. So going back to Gen Chem 1, just remember that you have a metal, and depending on how many valence electrons there were, so remember the Bohr model, if there's however many, up to 8 on the outside, that's going to be acting as your valence electrons. So those valence electrons are acting as the anion. So anions are a negative charge, and cations are a positive charge. So that metal on the inside is acting as the cation, and its valence electrons are acting as its anion. So that gives you an example of the electron C model to our right. And it's just showing 2 examples, group 1 metals and group 2 metals. So group 1 metals, that's going to be column 1, like for example, potassium. They have a +1 charge, and group 2 metals will be column 2 with a charge of +2. So the metal itself is going to act as the cation, while the anion is just coming from its valence electrons. Some more information about metallic bonding. These are composed of atoms in a very orderly array. So just think of like having a structure of a metal by itself. The atoms in the metal have not lost their electrons. They're still there, but they're just acting as the anions in the metal. When molten liquid, so when the metal is finally heated to a certain temperature to go from a solid to a liquid, those metal atoms are still attracted to each other via metallic bonding, but the ions are less orderly and are mobile. So remember that a liquid is far less structured than a solid. However, there's still bonding there. It's just not going to be as strong as solids are. Also, metallic bonding is not broken until the metal atoms vaporize, meaning that it goes from a liquid to a gas, with each atom taking an appropriate number of electrons. And then lastly, metallic bonding gives metals their unique properties. So if you compare different types of metals to each other, their properties are vastly different. Just compare the melting point and boiling points between them. That's just one part of them that makes them so different from each other. So two properties I wanted to discuss before this section ends is malleable and ductile. So if the metal can be hammered or bent into different shapes without breaking, that's considered malleable. A good example of this is gold. Gold can be changed into any shapes really. The more pure it is, the more malleable it is, which is why we like to combine gold with different metals to make it stronger. For example, if we're comparing 10 karat versus 18 karat gold. 18 karat gold is really pure, but it's just going to be more malleable than 10 karat gold. Next will be ductile. So if it is very malleable, we can actually turn it into long, thin wires for our use. The reason why is because we can use it to conduct heat and electricity. That's possible because the metallic bonds do not have a specific direction, and those electrons can flow within whatever shape the metal takes.